So anytime we use the word basis, and this goes for spanning set also, we should always say basis for what? These four vectors B in the set B are not a basis for four-dimensional space. But they are a spanning set for something, right? They're a spanning set for their own span. Right? So if I took these four vectors in four-dimensional space and I took all their linear combinations, according to the reduced row echelon form, we would get a three-dimensional subspace of four-dimensional space. And so it spans some three-dimensional space inside of four dimensions. And there probably exists a basis for that three-dimensional space. We would just have to find what that is. And that's actually the next thing that we're going to do today. If you give me a vector, a collection of vectors that has too many vectors in it to be a basis, how can I figure out which ones I can throw away and how many of them I need to throw away before what remains is now not just a spanning set, but a linearly independent spanning set for the thing that we're trying to span. So that's ultimately the goal. And anytime you use the word basis, you should always remember to say basis of what or basis for what. If you just say this forms a basis, then that's ambiguous, right? Because everything within everything we can find a basis for the thing that it spans, but that might not always be the same thing as the thing that we're trying to span, I guess is what your question kind of gets at. When we say that, let's say two vectors in three-dimensional space span a plane in three-dimensional space, there are a lot of different planes that they could be spanning, right? Determined by, if you like, for multivariate calculus, which normal vector that we select, right? But if it's a vector subspace, it has to pass through the origin, right? So the set of all vector subspaces that are two-dimensional inside a three-dimensional space is the set of all planes that pass through the origin. So we have a whole bunch of different ones. And each one looks just like R2, right? We could set down a basis of this subspace that gives us a coordinate system on that plane that makes that plane look just like the xy plane, where we could take the xy coordinates to just be coordinates along our basis vectors that we select for this plane. But that doesn't make it exactly the same thing as R2. It kind of makes it a copy of R2 living inside of R3. In a sophisticated sense, when you do geometry in mathematics, especially with higher dimensional objects, you have to kind of select, all right, so I have a higher dimensional object to study. What dimension do I want to embed it within in order to study it? We can study a two-dimensional plane just in and of itself, and that's usually what we think of as the xy plane. But we could also put that two-dimensional plane inside of a three-dimensional space and then consider, all right, how is it oriented? What are its properties with respect to the rest of three-dimensional space, even though it itself is still just a two-dimensional plane. So the question is, if I have a set of vectors and I can tell that no vector in that set is a multiple of any other vector in that set, is that enough to give us linear independence? And my claim is that it's not. And let me show you an example of why. So let's get our plane that we were working with before back up here. So x plus 2y plus z is equal to 0. Here it is. Let me put three different vectors up here on this plane. So maybe, what did we have before? Negative 2, 0, 1. That's one vector. And then negative 1. Oh, sorry, that doesn't work, does it? No, negative 2, 0, 2, I think I would have to do. So there's one vector. And then I'll make my second vector 0, 1, negative 2. And then I'll make my third vector. Let's see, what should I make my third vector? How about negative 2, 1, 0? So here are three different vectors. And we can kind of tell that none of these three vectors is a multiple of any of the others. Right? How can I tell that from the picture, by the way? These three black vectors, no one of them is a scalar multiple of the other.
They're not parallel.
Yeah, no two that I choose are parallel. No two of them lie in the same line is another way to think about that. And yet, how can I tell that these three vectors form a linearly dependent set? Why are they for sure not
Same
linearly
plane?
independent? Say again?
They all lie in the same plane?
They all reside in the same plane. In fact, I selected these vectors in such a way that actually one of them is just the sum of the other two. That if we just draw this parallelogram right here, this middle one is actually the sum of the two outer ones. So yes, it's a great question, and if only life were that easy, we would look like that futuristic space world in the memes, right? If only it were true that being pairwise, not parallel, were the same as being linearly independent, it would be a lot easier to discover linear independence. But alas, that's only the case for sets of 2 vectors. As soon as I have 3 or more vectors in my set, we can have the possibility that one of them is a sum of the other 2 or something, and that's not going to be detected by just looking for parallel pairs. So just scalar multiplying a vector is one way of getting something that's not linearly independent. Just adding a pair of vectors is another way to get vectors that are not linearly independent. But also combining those two, right? Taking a general linear combination. 3 times one vector plus 1 times another. Or negative 0.4 times one vector plus, square root of 2 times the other. Right? These are all valid ways of finding sort of a third vector that's linearly dependent on the first 2, right? And that's the most general version of it, because that is kind of the most general kind of operation you can do in linear algebra, is take a linear combination. Just take sums of scalar multiples. And in any set of vectors where a sum of some subset of them is equal to, a linear combination of some subset of them is equal to another one of them, then we have a redundant set, a not linearly independent set.